first of all, you have a homework that you can download from my web page. Okay. Work 2. Go to courses, start, and then PDF available, you can download. Okay. The due date is that should be classes are cancelled on Friday, is it? Huh? Huh? No, afternoon. So we have a lecture in the afternoon. We have an extra lecture of the weekends. I will let you know. Last a few lectures. Okay, so let's get started. Remember, we talked about this so-called relay fading. We came up with a model for short-term relay fading. Again, revisit it once again later, but let's switch to more accurate description of the wireless. Okay. What we have is we are going to transmit the x of t, the information carrying signal. Okay. Then what we receive is y of t, and then there is this channel in between with an impulse response h of t. Okay. Okay. So in other words, we can rewrite this as 1, put x of t, output y of t, then we have a channel x t comma tau. We'll come to this in a moment. Channel response could be a time varying channel response. Okay, we model it as a linear system, possibly time varying channel impulse response. What does it mean? Let's say we measure the channel impulse response. Let's say channel is varying slowly. Clock of, let us say, 1 millisecond. Send in unit impulse and you measure the response at the output. You get, let us say, h of tau. That is the channel impulse response as a function of. But as you very well know in wireless systems, as the users move around, the channel characteristics may change slowly with time. Once you measure in the next 1 millisecond, maybe change compared to the previous time over which you measure the channel. So what causes these variations? Well, multipath is inherent to wireless systems, and there is always what is called Doppler, which will talk about it. Doppler causes time variations. Even if the user is stationary, still you can expect the channel impulse response to vary because the surroundings are not stationary. Always some movement. Transmitter. That's right. Be something moving. If there are trees, the leaves are moving around. Something is changing always. Okay, even if the user is stationary. So there is always an effective speed at which the user is moving. In any case, the impulse response h of tau can vary with absolute time t. Therefore, we denote it as h of t tau. But if the impulse response is non-time varying, let us say, then we would simply represent it as h of tau. T denotes as the time variation. Okay. Luckily, in wireless systems, the entire system can be modeled as one of a linear time invariant system or possibly time varying system. Hopefully the variation with time is slow enough for us to handle the whole entire. For a snapshot of time, for a block of time, you can model the response as one that is not varying. That is the case then. Okay, so then what is this h of t tau? This h of t tau. H of t tau, or first I'll write the case where the impulse response is not varying with time at all, and then I will generalize. Okay? H of tau, in the case where it is time invariant, can be written as I amplitude AI delta tau minus tau I. Well, if the summation over a finite duration, then it is finite impulse response, FIR. It is FIR because summation is dominated by it takes finite time. So, what is the justification for this model? Well, you have sent, if you send delta of t, what would you observe? Of t you would observe. So what does it mean? You send one impulse. Wireless nature of the channel is such that channel takes values and so on. Let's say this is tau equal to tau 0, tau equal to tau 1, tau equal to tau 2 and so on. It means you will receive many copies of the transmitted impulse arriving at different time delays. That's because of the reflections objects surrounding the transmitter. Of course, if there is a perfect line of sight in free space, obviously you'll have but the question here is that if it is a time varying system, then we can generally write this impulse response as h of t comma t tau, that is equal to ai, which could possibly vary with time. Therefore ai is ai of t, and delta tau minus tau I of t. Why is that tau I is also a function of time? Well, this is the impulse response at one given time, but these positions of these tabs could vary with time. This could be changing with time, and the amplitudes. And we further assume that this impulse response is independent of the frequency components of the signal. Time being, we'll assume that impulse response does not depend on the frequency. Okay? Okay. So if that is the case, what would be y of t if this is the general impulse response? Can you give an expression? What would it become? ai of t input is x of t. Therefore, this becomes tau I of t. Remember here, these are passband signals, not a baseband representation yet. What we transmit x of t is a passband signal at some carrier frequency. So therefore, the AIs are real valued quantities. Okay? Because these are passband signals. Now we'll come up with a baseband representation, an equivalent baseband representation for this system. Okay? Okay, these are band pass signals. This is a band pass signal. Okay. Let us say we want to measure, see, typically we measure the impulse response in any system, not at passband level. We always carry out all the operations in baseband, low pass band. Right? Most of the time work with. That is the case. We also want to know the impulse response in the baseband form. Right now, this is what the channel looks like. Its physical form. They're just coefficients A0, are not complex numbers yet. How the signals are. Nice thing about this entire representation is that we don't have to worry about the magnetic field, antenna type. We don't have to worry about all. Everything has been abstracted out into this impulse response, or captures everything. Okay? I would write all the Maxwell's equations. Okay, now more interesting to see this in the baseband form. That is, let us say write x of t, the passband signal, as real part of xb of t, which is the baseband equivalent of x of t multiplied with e raised to 2 pi fct. And now we should be comfortable with this, right? If that is the case, I can also write y of t as isn't it? Maybe y of t also has a baseband equivalent signal. If that is the case, I can rewrite this entire system model as 1 xb of t so I need to determine what is the baseband equivalent of this channel h of tau or h3 comma. Okay. Okay, that can be done. What we can do is we can substitute for x of t here, and we can also substitute for y of t right here. Okay, that is equal to summation over I ai of t. I would say that, don't worry about this t and this t too much, because it is only mentioned here case where we want to handle time varying systems, but not handle. We'll always take a block of data over which we'll assume that the channel is time invariant. Therefore, we can draw t safely. Okay, fine. X of t is known, so I'll write x of t minus tau a of t. That would be real part of t of t minus tau a of t, and e raised to j 2 pi fc, and t is replaced with minus tau a of okay. So we'll rewrite this here. Y of t is real part of yp of t e raised to j 2 pi fct, that is equal to remember ai is real, so we can take the real part out safely, right? AI is real because
we can take inside.
huh?
Inside.
Yeah. Take the real part here and move this inside, okay? Well, we can move this real totally outside of this summation. Okay? So this would be real part of summation I ai of t e to the power of minus j 2 pi fc tau I of t. Okay. What else is left? B of t minus tau I of t multiplied with raised to okay, 2 pi fc into this part, this part are comparable, right? Right? The real part of something if you use j to pi fc t. Okay. So if I have to write yb of t, then that would be the entire portion, isn't it? That would be summation over I ai of t e to the power of minus j 2 pi fc tau I of t multiplied with xp of t minus tau I of t. Agree with this? Not much here. We're just comparing term by term. Okay, we're just comparing this portion, and they should be equal. This I will write as ai t of t into xp of t minus tau I of t, where ai of t is defined as ai of t to the power of minus j 2 pi fc tau I of. Here we will come back now. Are we ready to define the baseband equivalent response? Can you tell me what it is? Summation over I ai b of t delta of t minus tau I of t. It's tau minus, right? Compare with this. Okay? Make sense? This is pretty much in the same form as the passband case, right? Therefore, the impulse response, baseband impulse response should be this. But what is the difference here? Only difference here is ai of t e to the power of minus j 2 pi fc tau I of t is what is appearing. Delta of tau minus tau I. So, this impulse response now a0 e to the power of j 2 pi fc tau 0 of t tau equal to tau 0 minus and so on, so forth. So in the baseband form, the impulse response is generally takes complex values, right? And if you write fc into tau I of t as theta I of t, then we can call it ai e to the power minus j 2 pi theta I. Okay. So we started with the passband model for a wireless channel where it is modeled as bunch of taps with various delays, a real valued channel. And its baseband form is pretty much the same channel except that the phase component comes into picture. Baseband it generally takes okay. And yeah, tau. Send an impulse at the transmitter, let us say, and you receive the first copy of that impulse attenuated by, let's say, A0, and after some time tau 1, let us say, some time, the second copy comes with an different attenuation. After some other time, some other copy. You don't know what this tap time delays are. That you have to measure. T is the time variation in the absolute time scale. Taus are the inter-tap delays on the tau scale. These are the inter-tap arrival times. Okay. If you want to call instead of tau, you want to call it t, then absolute t, you must change it to something else. But you can't do that because x of t is strictly a function of time t. Y of t is a convolution between t and the impulse response h of tau. Okay. Not done with this, but there is to discuss a very important concept. I'm still not talking about Rayleigh fading and all those things here. Not assigning any distributions for this. These are the physical channel where the weights are the actual attenuation factors experienced by the signal. And we're not talking about a narrowband system, we're not talking about the wideband system, we're not talking about anything. It is the actual description of the physical channel. And the taus could be whatever it is. These are the physical delays. Data rate of the system. So now, what we are going to do is, obviously x of t that we are going to transmit is going to have a certain bandwidth. X of t is going to occupy certain bandwidth. GSM it is 200 kilohertz. I mean, assuming it's a band limited signal. Not band limited signal, you truncate it. Still, assuming a band limited signal, X of t, the information carrying signal, has its own bandwidth. And at the receiver, one of the first steps that any receiver does is receives y of t, okay? Then it puts some sort of a it down converts the signal into low pass form. And then one of the first steps we always do is analog to digital conversion, which is sort of viewed as a low pass filter followed by a sample input. What we are going to do is we are going to take the baseband signal apply a low pass filter and take samples at the rate 1 over t, where 1 over t is the baud rate of the signal or the signal. 1 over t is intimately related to the bandwidth of the system. In the Nyquist class of signals, 1 over t is indeed the bandwidth of the system. If you don't want to operate at 1 over t rate, you can operate at 2 over t or 3 over t or some other rate in between. That's fine. They are called fractionally spaced receivers in TDMA systems. If you operate the receiver at more than where the taps are, where the signal, the time delay, the time spacing between successive samples, if it is greater than t, if it is less than t, you call it fractionally spaced. We'll discuss that later on. The point here is, at some point in the receiver, you might apply, let's say, a match filter or some other receiver, right? An equalizer, sort of operation. But in many systems, what we do is we bring the signal to low pass baseband form and then put a low pass filter. Let us say that limits the signal to the effective bandwidth W. W is equal to 1 over t. Then collect the samples at the output of the receiver. And these samples, discrete time samples, convey the same information as that of the original analog information carrying signal XB of t, which is in its baseband. Then you can use DSP operations to make. If that is the case, if you are going to discretize the signal at some point, what would be the impulse response of the discrete time signal? Not a discrete time signal, everything is analog form, right? Everything is in analog form. This is, even the impulse response is in its analog form. But if you are going to come up with a discrete time representation of the information carrying signal at the receiver end, you have to describe the impulse response. Time form, whether it is t spaced or t by 2 spaced. Two-dimensional signal actually, and tau and the x amplitude, and input signal is x amplitude. We are missing the some signal. Nothing is missed here. Let's see. There is expression for y of t. There is expression for yb of t. Yb of t is summation over I. Ai of t, if it is time invariant, this part is gone. Xb of t minus tau I. If it is time varying, tau i's are varying with time. Fine. Y of t is fully captured in its correct form for a time varying system with time varying impulse response. See that? Out here. But of course, if the time variations are too rapid, then it's sort of not such a desirable situation. The time variations are on the order of, let us say, if the signal is transmitted at rate 1 over t, if they are on that order, then okay, it will be very difficult for the receiver. Usually these variations are so slow that for a chunk of time, for one time slot, you want to transmit a packet. Over the duration of this packet, if these variations are negligible, then we can happily go this and this. Then all we have to do is estimate this A of B. Not going to change over the duration of the packet. Right? So most of the exercise that we are going to deal with first, steps will be time. Okay. Now we'll come to this so-called discrete time baseband model. These are two things you have to remember always. Any signal we transmit is analog in nature. The channel always is analog in nature. Nothing. Yes. Channel may take in this particular form, but we have not resolved it, this channel, into discrete time form where we take samples at fixed intervals. These tabs are spaced at arbitrary Okay, so what we will do is take xb of t, we take a strictly band limited signal, limited to certain bandwidth, right? Then observe yb of t, and we'll take samples of yb of t over t equal to, let us say, mt or something like that, capital T duration. Now, if you want to understand communications, to understand the nature of the channel, and the channel, and the characteristics of the channel, then understanding the channel also involves understanding multiplier. Take X, the information carrying signal in its baseband form, an arbitrary signal. The bandwidth here, W, let's say it is equal to 1 over T, or T equal to 1 over W. Arbitrary baseband signal xb of T can always be represented as with this. That comes from 7 IQ sample. What have we done there? T of T can be represented with a set of points x of n. Samples x of n pretty much contain the same information as xb of t, and the function is, it's an interpolating It's an orthonormal. Orthogonal basis. Okay. What is x of n here then? How x of n and x of t or xp of t are related? P of t taken at t equal to nt or n by w. So this can be written as xp of n by w, or it can also be written as xp of n. So alternatively, we can write xp of t as okay, I'm just writing this in different ways. One as a function of capital W and other as a function of. Okay. Given xp of t, what is the relationship between y of t and xb of t? Yb of t is equal to summation for I ai b of t p of t minus y of t. Remember this? Derived it? Huh? Now we replace this xb of whatever it is with this. Okay? So that would be xp of nt will write as samples x of n multiplied by sync w t is replaced by minus y of t yes and here. Okay. Now we'll move this summation outside of n the b here baseband. W multiplied by T minus W into tau I of T minus okay. Okay, this is YB of. We haven't done much here except that we plugged in the expression for XB of T by using the amplifier. Okay, XB of T we expanded it. We wrote it as summation of X of n multiplied by E. Looks a bit cumbersome, but what are we interested in? We are interested in collecting samples at T equal to say M or M by W. Collecting samples of the received signal the assumption here is the transmit signal is strictly band limited. In fact, we should have put low pass filter here so that the noise will also be limited, but I guess we are not even considering the noise here. Sort of a noiseless signal. Therefore, directly take the samples because the signal is band limited. Transmit signal, therefore, the receive signal is low. Nevertheless, we can also put a low pass filter here, an ideal low pass filter. And what is the bandwidth of the low pass filter? Put an ideal low pass filter with perfectly black spectra minus W. Then we can take the samples equal to, and as you should understand that inclusion of this low pass filter will not in any way alter the frequency content of XB of T. Right? For our purpose, for the current purpose, we'll just replace T with T equal to MT because this filter is not going to alter the characteristics of the baseband signal, but it will limit the signal to that particular band. So if there is a little noise added in the front end, that will be limited. And the equal impulse response will also be limited. Impulse response will also be. That will be the case in any way because the baseband signal itself is limited. So it is zero outside. So multiplying with a channel, with a non-zero channel outside the boundary is minus W by 2 plus W by 2. Right? Because the original signal XP of T and let us say the channel has characteristics between minus infinity to plus infinity, but when you multiply them, what matters is the product XB of F multiplied by H B of F, and we are interested in the range minus W by 2 plus W by 2. So in any case, the effect of the channel gains outside the range is not of interest to us. But therefore, whether you have this or not, this only limits the noise in this. Okay. So what we will do is, we'll assume that this filter is not going to alter the characteristics of the received signal y, because we are considering noiseless case. Yb of t, input is also Yb of t, and at this point we take t equal to, samples at the rate t equal to m capital T, where capital T is equal to 1 over. We'll define y of m, defined as y of t, with t equal to mt or m by. Okay. What we will now do is, we will replace t with mt or m by w, entire expression. So y of m is no longer a function of the t will vanish. We have taken the, we have discretized the signal at this point. So what we have here is y of m. You write y of m. Okay, we'll do it here. Y of m is equal to summation over n of n summation over I of equal to mt or m by w. I am multiplied with think w into m by w, right? That gives me m minus put the n here, m minus n, okay, minus w into tau y of t is m by. No, of course, it's a bit cumbersome to have this little function here if it is time invariant system. How? I think there is I here. How? I. This part will go away. And we'll write the time invariant. Okay. Now, I will call m minus n equal to L. We'll introduce a dummy variable. Yes, we'll redraw this picture later. A of m, I'll rewrite it here, is equal to summation over n. N is equal to m minus L, x of m minus L summation over I is think L minus W into tau I of Summation over. There is no n anymore. Summation. Thank you. Entire this I will call it H L of M. Therefore, this can be written as L x m minus L H L of M. See? Where H L of M is equal to summation over I A I B of M by W sin L minus W into tau I of M by W. We're going to make this look a bit more simpler in the end. And Y of M is the convolution between X of M and HL of M. Remember, M is the new time index here. M is the discrete time index. Why is that? We took samples at t equal to m. The new time index. Okay. Now, if the system is time invariant, quite a bit of a simplification. What will be dropped here? What would be dropped? What would be dropped here? Time invariant H L of M. It's no longer a function of M anymore. M is the time index. H L of M, where M is the time index. If the system is time invariant, the channel impulse response should be independent of the index M. Time index. That would be H of L, and that would be AI of B, and the brackets, whatever is in the bracket, the function of M, therefore it is independent of time. So we don't write it as AI of B, which is a constant, sin L minus tau I into W. You agree with that? Tau i's are constants, AI's are constants. They are, constants in the sense they are not varying with time. Tau i's and AI's are not function of time. AI of B is AI e to the power of j theta I. By theta I. That's how we do. Okay? So, the effective impulse response, now what is H of L? That resolved at you may say, why do you want to start with L equal to 0? You can start with any function of AI e to the power of j 2 pi theta I. Indices I, tau I, and they are a function of the product tau I into W. Tau I into W is tau I by T. So you are going to resolve T-spaced equivalent channel from the original channel. But this T-spaced channel, the spacing is what? What is the spacing? Seconds. Between any two taps, the spacing is T seconds, right? Tau is gone. It is now resolved. Thing is at the rate. Tau I's are analog. Now everything is now resolved into T-space channel. T-space. The receiver is operating at T rate. Channel impulse response. So you will see, observe taps. What are these taps? Well, these taps are related to the original channel through this sync interpolation. Okay, what does that mean? Well, all the taps actually do contribute to any HR, right? But now, how do you say narrow band channel, wide band channel? Wide band channel has many taps, many taps. Narrow band channel has only one tap. Okay, let's take the narrow band case. Take the narrow band case. What is narrow band and what is wide band? Well, narrow band and wide band is decided by W, how large or small W is with respect to tau I. In this case, we should take tau I max. Right? The delay spread is there. We should take the tau I max. Let us say the original channel. Let's look at hypothetical here. The original channel. Let us say the original channel, the baseband channel, looks something like this. A0 for j 2 pi theta 0. A1 e to the power of j 2 pi theta 1. A2 e to the power of j 2 pi theta 2. This is tau equal to tau 0, tau equal to tau 1, tau equal to tau 2, and then we have tau equal to tau n, some number an e to the power of j 2 pi theta n. Let us say tau n is much smaller than t, or in other words, t is greater than, higher than tau n. See what's happening here? But t, you are sending data symbols at t, so possibly an the xn's is you are sending information at the rate xn. So that is the rate at which information is sent. Xn could be BPSK symbols. Okay. But if this t is much larger than the maximum delay component in the impulse response, the maximum is tau n. From the point of view of the receiver, how will this look like? Tau I by t. T is infinitely large compared to tau I, rather, or any tau. Then this tends to t in the limiting case as t tends to infinity. Of course, this hypothetical saying t is very large compared to any tau I that you see, then goes to 0. If that is the case, h of l is equal to sigma I ai of b, and ai of b is into sync L. A of b is e to the power of j 2 pi theta I into sync L. Now you tell me what is the channel characterization here. Sync L is unity for L equal to 0 and it is 0 elsewhere. That means h of 0 is equal to summation I, ai e to the power of j 2 pi theta I. For any other tap, is what is this? It is a single effective tap. T is very, very large compared to the delay spread of the system, or the maximum encountered component, delay component, a significant energy. From the receiver point of view, all these taps which are analog in nature appear as a single effective tap in the form. What is the distribution of H0 now? AIs are random, theta I's are random. Can be written as R e to the power of j theta in case where I has a lot of components, and usually that is the case. That is the case. That is not the case, then it will be not all realistic. We have a lot of taps, and they are all very close to each other compared from the receiver point compared to the signaling interval. Capital T is very large compared to these taps. All these taps will merge into a single effective tap, and the envelope will have Rayleigh distribution. Theta will have uniform distribution. We call it a flat fading channel or narrow band flat fading channel. Narrow band flat fading channel. This is one extreme. How it relates to what we derived yesterday. Narrow band flat fading. Okay, let's take the other extreme. The other extreme is T is comparable to the delays. T is comparable to the delays, and I am going to consider hypothetical channel just to simplify the matter. And I am going to consider the situation where the delays are such that I'm talking about the version analog. I am going to construct a hypothetical channel where the taps are occurring at T space. Of course, it may not be the case, but I am going to consider this. That is the case, the impulse response would be basically this at T space. Because we are going to resolve them, right? But of course, this will not happen in real life. Okay. Of course, this is an intersymbolic. The response would be convolution of this profile with the transmitter. But in real life, what happens though is that you will never have the situation where channel will be following any of these nice profiles. Usually, channel taps occur like this. They occur in clusters. All these clustered rays will contribute as one effective H. Of course, there may be contribution from others also, but if these are occurring at T, 2T, 3T, NT, and there are other rays in between, and let us say these rays are all clustered very closely, all these rays will contribute to one effective tap which has Rayleigh distribution. All these rays will contribute to another tap which has Rayleigh distribution, and they are statistically independent of each other. HL could be statistically independent of L if at all you get clustered rays and they are all at here. But of course, in some cases, I have a tap here, then it contributes to both H0 and anyway, the point here is ultimately, H of L's can be represented as tap with Rayleigh distribution uniform phase, but they could be correlated. Sometimes we use the model where they are IID assume the average energy of each step. Model we use. But in reality, the gains are 100. Okay, so I'll give you a slightly different interpretation before we close this lecture. That is, looks a bit cumbersome to look at H of L with sync interpolation. Okay, it's not so convenient to visualize this. So I'm going to give you a frequency domain interpretation, which is always okay. Remember HB or H of tau is baseband form takes this AI of B, that is AI of e to the power j theta I, so there is a j 2 pi theta I delta tau minus tau I. This is a baseband channel representation, right? What is H of F? H of F is Fourier transform pair with H of tau. Okay? That is the case. H of F would be summation I AI e to the power j 2 pi theta I e to the power j 2 pi f tau I. Is that right? I'm taking the Fourier transform of the minus. Okay, there is minus j 2 pi minus. Okay, it doesn't hurt us too much, but let's see. What is the range of f? Okay, as far as this definition is concerned, f can go from remember, we are really interested in h of f that is bounded between minus w by 2 to plus w by 2 because we for the reasons we are explaining, right? So we are interested in this h of f in the range minus w by 2 plus w by 2. Okay. So there is this h of f but we are interested in the range not a precise representation, but we'll write it. What we will do is take h of n, which is Fourier transform pair with h of f, where it is strictly bounded between you write like this. This is going to be, well, I should put something. It's going to be periodic, right? This is discrete time. It's going to be periodic period double. What is this h bar of f? What I want to do here is portion we take, okay, and let us replace f with let's take n points h of f. H of f, we divide this into n. We divide this into n points, and this becomes pi tau I into I by e. The range of I is well, it should range from minus 1 over tt to plus 1 over 2t. Minus n to, I will get n minus 1 point. Okay? So it will become a 2n point. Okay. Now this is f. Now we discretize h of f. Now we take the IFFT of h of. This is a function of h of I, right? Take the IFFT of h of I, that gives you h of n. So what do you get h of n here? That is nothing but the impulse response in time domain, of course, truncated to n taps. So it is time limited to n taps. As capital N goes to becomes larger and larger, you get. So this is one way of observing the time domain impulse response using FFT. HFF is defined. Take the portion of interest to you. Take some, not n points, 2n I think here. Take some number of points and then run the IFFT. Then you get the impulse response in time domain. And you can already see that impulse response is a summation over I, ai to j minus j by theta I with complex exponentials. Now you can see that depending on the values of tau I, you can resolve. Now the parameter that matters is tau I by t. If tau I is very small compared to t, then you will end up with a single tap as usual. Or if tau I is comparable to t, then you end up with many taps. So what will be h of n that you will observe? You observe gaps of this one. That depends on the bandwidth. So wideband systems, if the bandwidth is high, like let's say 20 megahertz, and if the delay spread is on the order of microseconds, then you can resolve it into a number of times. On the other hand, narrowband systems like a 30 kilohertz channel, the old USTDMA system, practically appears as a blank channel. Kilohertz. Gaps, the margin. So we will see depending on the multi-path resolvability at the and wideband are measured with respect to delay. Okay, so we'll take a few homework exercises